Freeform lens technology has revolutionized our industry, allowing us to create increasingly advanced and customized lenses. What makes freeform lenses better than conventional ones?
The visual quality of a lens decreases as we move away from the optical center due to oblique aberration, which arises when light rays enter the lens at an angle. The light rays refract in the lens, preventing them from focusing on the fovea and generating power errors.
The wearer perceives a blurring in the peripheral area, which increases as we move away from the center of the lens, leaving a reduced area of clear vision. IoT's digital ray path lens calculation technology significantly reduces peripheral blur. For this purpose, it considers the wearer's parameters and the position of the lens in the calculation of each design. Ray tracing simulates oblique aberrations for each gaze direction and associated focal distance by modifying the back surface of the lens to give the wearer the best vision at every angle. In this way, we achieve a significant reduction in the effects of oblique aberration. The improvement is obtained with advanced geometry, but it cannot eliminate peripheral blur for wearers by itself. The new version of the digital ray path technology gives us the answer to overcoming any geometrical limitation. IoT includes, for the first time in the ophthalmic industry, a key aspect in the calculation and minimization of oblique aberrations, the wearer's accommodation.
Accommodation is the natural mechanism that allows us to focus accurately at different distances. Up until now, custom lenses were only optimized to view objects at a single associated distance. However, by stimulating and relaxing a small part of their accommodation, the wearer can focus sharply over a range of distances at the same point on the lens without moving their eyes or changing their gaze direction. This range of distances is known as accommodative object space.
Digital ray path can now simulate oblique aberrations in the accommodative object space, considering all focusing distances and gaze directions, thereby achieving a more accurate and realistic optimization according to how wearers will use their lenses. In addition to the inclusion of the accommodative object space, it uses an innovative mathematical model that intelligently minimizes oblique aberrations, considering the wearer's accommodative power. To understand this, it is necessary to know the components of the error induced by oblique aberration and how the visual system perceives them.
This induced error is composed of a cylindrical power error, which generates distortion, and a spherical power error, which produces blur. The visual system reacts differently to both errors. The eye has no mechanism to reduce the cylindrical error and perceives it as distortion. The use of a small fraction of accommodation can cancel out the entire negative spherical error component.
Digital ray path can now maximize the reduction in cylindrical power error and keep the residual sphere component, which is the one that can be easily compensated with accommodation. The result is a fully customized lens with a more efficient compensation of oblique aberrations that offers the wearer impeccable visual quality and precise, comfortable focusing.